assignment 3, we were supposed to tell him what discussion
So are you graduating?
Or the teaching
Yeah, the track
Those
is.
are assignment coffee courses.
That is?
Yeah.
They posted last night. I submitted it late because I got home at like midnight and I turned it in at 12:18.
What should we submit?
Oh,
Do you have any, like,
I just downloaded the form and resubmitted it. Because like in the files you can see the assessment. Oh yeah, yeah. I resubmitted, but you have to submit a PDF in order to submit your
But you make comments on the
the green one, right?
Yeah.
Oh well, I'm so confused now. Yeah. I was get home like after midnight. I was supposed to do homework by midnight. I should ask him. Huh? No, yesterday I was doing a bunch of errands, and then I said yes to watching a movie, and then movie took longer than I thought. But yes, usually I have skydiving practice on Tuesdays. If I don't pass them.
He doesn't put those levels up until after classes.
Yeah.
I think those homework sheets, you probably never check it. You just check it.
I mean, it's like it's a pedagogy class.
Yeah. So we can't write it. How about we write it?
An example where this movie was too much food.
Would you want to?
No, it's mostly that I just didn't get the juice. I should have said yes. But they made it sound so good.
Good team.
Logan Lucky? They're like, oh, it's made by the same people who made Ocean's 11, and it got a 93% of Rotten Tomatoes. Was it good? It was pretty good, but yeah, it's like really, it's like the same pace as Ocean's 11 though. It's like slow. Logan, it has Channing Tatum in it. That was another reason why. But he was not shirtless, so why fight you? Microaggression, macroaggression.
It's like
Well, he's not here, so what does that mean? I was there for his outing. But it was a pretty good show. I mean, talking about the movie. I just really like heist movies, you know? Like Italian Job.
Actually, after I take this course, we talk about microaggression. When I see the film, I see there's a lot of it.
Which one?
All right, so let's get started today. We're going to change the schedule up a little bit. So we'll start actually with the mock presentations, and then take a break. The lecture today is very, very short, so that might be a good thing to do at the end of the break and kind of change the cadence around. And then we'll finish with some more mock presentations. So that way you don't end up getting, like 90 minutes of mock presentations straight through. So a couple of other things. So for those of you who either signed up for Tuesday and Wednesday and we didn't get to you, or you weren't able to make it, or if we don't make it today to you, what I'm planning on doing is we just don't have enough class time to get through everybody, especially with the over-enrollment. I think we're like trying to get to enrollment of like 70 or more, and it's a little bit tough. I'm going to take the groups of, I'm going to basically kind of go through the list of people, everybody that presented, and whoever wasn't able to present, we'll put you guys into smaller groups of maybe 5 or so. You can get together for about 30 minutes outside of class and just have kind of the same thing but on a smaller scale. And so hopefully, we'll keep it small so it doesn't turn into a huge time sink for anybody. But that's the plan. So I'll go through the list and figure out who didn't present and cluster you and find a time that works Yes.
Can those people leave 30 minutes early today?
Can they leave 30 minutes early today? Well, it'd be ideal if you didn't, but if you need to leave, I know it's a little bit unfair, and I actually screwed up the protocol, by the way. So I originally said people who couldn't make it to all 3 days should put their name at the top of the dash line, and they'd go first. That was optimistic, thinking each day we would be able to get through the list. I realized in hindsight that that was actually exactly the wrong protocol, because the people who couldn't make it to all 3 days now not only doesn't have to go to all 3 days, but the people who did go to all 3 days now further gets penalized by having to go and have a group meeting. So that was a stupid kind of, poor thinking on my part.
Is it possible for us to just break off into small groups in class?
Today, you mean?
Yeah, and just have multiple presentations.
Well, we could split the class in half. You know what? This is a great idea. Let's take a vote. Can we find another classroom that we can pack half the class in today? All right. Who wants to volunteer to go see if we could? Oh, just partition the actual classroom. That's an interesting idea. Is somebody going to freak out if we do that? It's open next door, too? I think that might be a little better, just kind of spread people out a little bit more. Okay, so in that case, we're going to change it up again now. I should probably just do the lecture, and then we should probably break, because then trying to get everybody packed back in here halfway through seems a little bit more painful. Right? Yes? Okay, so first, generally you should never have votes in public, because people who don't like this idea might feel bad about voting one way or the other. But I'm going to ignore that. Would people like to do this? Would you prefer to split into 2 groups and do it that way rather than having to break out into groups of 5, meet outside of class? So I see. Okay, a lot of people seem to say yes. Before we just agree, I do want to hear dissension. If there are legitimate reasons to not do it, does anyone think we should not do this? There's some downsides to it. There are some obvious downsides, so we take this opportunity to discuss what they might be for 30 seconds. So what are some downsides of breaking this into 2 groups right now? Yes? So you might not get some feedback from some set of the group. Of course, the alternative is that you're in a really small group. Someone else said you don't get feedback from me, which is true. Of course, you don't know if I would show up to all of your 30-minute groups either, and I hadn't committed one way or the other. So it's so any other downsides? Yes.
Unless you have a second microphone, there's not going to be a mic.
So you're not going to have the same kind of stage presence without a second microphone. You don't get it videotaped here. However, we could still do like a phone video and upload it to B courses. Okay, so that could be something that each person does in the other room.
So 521's booked at 6:30. So if we're going to use it, we should go now.
Okay, so all right, let's try it slightly differently then. Why don't we break, go to 521, and then come back at 6:30. We'll reconvene, and I'll just spend a few minutes doing lecture, and we'll just kind of, maybe that's the best thing to do to make use of the most space. Does that sound good?
Yeah.
The label is also just busy. They didn't state what they're doing, so if they're not there, we should just take it.
Can you call out the names of the people who should present over there?
Yes. So if your name's on this list, stay in this room. And that should be roughly. So whoever presents over there, you should keep track of who they are, and I will come over and take a picture of the whiteboard. And yes, honor system, but also somebody needs to agree to sign up and take a video of each of these talks. So do a video on your phone and upload it to B Courses. I'll open up an assignment so you can upload the media. Okay? So make sure every presentation is captured. Sorry, we gotta improvise. And
Your name is not on the list.
if your name is on the list, definitely stay in this room. Okay? If your name is not on the list, yeah, flip a coin.
Okay.
Actually, I missed the first class.
Okay.
And I didn't register for any of these 4 days.
Okay, that's fine.
Yeah, so should I present today there?
Yeah, I would go over there and plan to present.
Oh, fine.
Okay, so Velmik, are you Velmik? Okay.
So normally I have slides for this presentation. There's a lot of numbers, so I might use shorthand or something to write it on the board. Can I just talk really loud, or is the microphone even? Okay. Let's see. All right, so today I'll be talking about Fermi estimation, which is basically a wonderful tool you can use to make accurate estimations when you have no data whatsoever. So the way it works is you basically take a problem and you break it down into multiple sub-questions. You don't need to know the answers to these sub-questions, that's the beauty. But the more sub-questions you break it down into, the more accurate your answer will be. And this is because when you're multiplying multiple factors together, your overestimates will tend to cancel out your underestimates. So even if all of your inputs are wrong, the output will still be of the right order of magnitude. So let's do a quick example, which is something that I did in 5 minutes. Yes. At home several months ago when I actually made this lecture. But it is something that you could do in 5 minutes on your couch with no preparation. So here what we're going to estimate is the amount of CO2 produced by all the cars in the United States. So that's a pretty hard problem. And like, I have no idea what the answer is. Well, I do, but I had no idea what the answer is. But using Fermi estimation, we can break down into a couple sub-questions and then bullshit our way to victory. So first, let's say, how many people are there in the US? I have no idea. Maybe it's 400 million. And OK, so out of those 400 million people, how many have cars? I don't know, maybe a quarter of them? Yeah, 4 people, or oh, no, I broke it down even more. So how many people are there in a family? Maybe 4. And each family will have maybe 2 cars. So that's now, we have all the cars in the US, possibly. But how much do they actually drive? Let's make this up too. So let's just say, I don't know, my parents' commute is 40 miles. So let's just say all of these cars drive 40 miles a day. And how many days are in a year? Let's just say 350. I I don't know. So 20 miles per gallon is like a kind of average value for cars. And let's pretend gas weighs the same amount of as water. And let's assume that all of the gas, when it gets burned, turns into carbon dioxide. So that's 2,000 lbs per ton. Okay.
Is there an answer?
Yes, there is an answer. So yeah, we can just multiply all these factors together using dimensional analysis, and we'll get maybe an answer. So if you multiply all these together, you get 700 million tons of CO2 a year. So the actual answer is 1,200 million. And this comes from a governmental agency that spent literally months answering this question, and I got within 50% making numbers on the spot. So Fermi estimation, it's great.
So, positive feedback.
Yeah.
I thought he spoke like really loudly and really clear, which was really nice. Like nothing was, even though there's like a lot of numbers, I feel like he went through everything pretty systematically, so that was great.
And this is just relevant for your presentation, but thanks for writing down the units for each number.
Yeah. Normally I have a slide that just has all these numbers on there. And that's, I think, less confusing.
Other feedback?
It was very entertaining and engaging. Got our attention.
Okay. How about constructive feedback?
I think in the beginning when you were explaining what it was, it would have been helpful to jot down a few notes on the board.
Yeah.
It was a little hard to follow in the beginning.
It's a little difficult for me to see the notes on the board, so maybe a different color marker or larger writing.
Yeah, and I mean, normally this would be on a slideshow. I wouldn't do this on a board. But
Other feedback? Okay, great.
oh, who's next?
Yeah.
Oh, Richard Grace.
Yeah. Hi, everyone. I'm Ying Liu. I'm from Material Science Department. And in our lab class 3, we will use material calculation technique called X-ray diffraction to study the crystal structures. And today, I will discuss something about X-ray diffraction and Bragg's law, which is essential to this technique. Yeah. So in X-ray diffraction experiment, we start with an X-ray source, which can be used to generate X-rays. And the X-rays will hit our sample at a certain angle, theta. And we will use a detector to detect diffracted X-rays at the same angle, theta. And the sample we use in the lab is silicon crystal, which is an important semiconductor material. And in the measurement, we will scan the angle theta and use the detector to analyze the intensity of the collected X-ray. So the result we will get is something look like this. We plot the intensity we collected versus the theta here. We will say something like this. And the feature is that at a certain diffraction angle, we will have a peak in the intensity. How to understand this result? We need to know Bragg's law, which is shown here. And we should take a microscopic view of our sample, the silicon crystal, which is formed by a set of atomic planes with a distance d. It's a atomic spacing. And within these planes, the atoms are aligned, arranged in a periodical way, like this. And the incident X-ray can be represented by like rings, and diffracted signal can be represented by rings like diffracted from like each planes, atomic planes. And the X-ray from the X-ray source, we will think it's a plane wave. So that means they are coherent, like this ring and this ring. They are the chops, the peaks and the chops. Sorry, it's not a bad drawing here. The chops are aligned, so they are actually in phase. But for the outgoing waves, the phase can be different. Why is that? Because we call this ring 1, and this is ring 2. The ring 2 travels an extra distance here, so the phase of the ring 2 and ring 1 could be different. And to generate these peaks here, we need to have certain conditions of the outgoing rings, and which is called constructive interference. So should I stop? Okay.
So remember, important lesson: stop when the bell rings. Okay, so positive feedback.
I like the drawings and the diagrams, and it was pretty clear to understand.
Other positive feedback? How about constructive criticism?
I think in the end, with the board on the left especially starts to get like a little bit crowded. So
Yeah.
if you're taking notes, it would be kind of messy.
It's a bit hard to read some of what you've written. It's fun because you say it, but if someone is trying to catch up with you,
Yeah.
some of the things are a bit difficult to make out.
Most of the time you're facing the board.
Okay.
So the balance.
Yeah.
Other comments? Thank you.
Oh, there's one. There was one right there. Hello everyone, my name is Cameron. So today we're going to talk about a form of encryption called block ciphers. So in encryption, we have some person, it's called Alice. Oh, I just spelled Alice wrong, don't worry. Sending some kind of message, M, to another person, Bob. But over this communication path, we are worried about people who could be listening in, or eavesdroppers, who we may call Eve. Listening in on that message right there. So when talking about encryption, we want to ensure three things. They are confidentiality. It's a long word. I'm spelling it wrong too. I'm going to guess that you can change. We want to ensure invertibility And we want to take input of arbitrary size. So this is where we have block ciphers. So the point of block ciphers, let me describe what they are. They are a algorithm. There's a lot of writing in this one. An algorithm. We're going to say a deterministic algorithm. That's the important part. I cannot spell in my head, guys. Algorithm on a fixed number of bits with a symmetric key. So there's a lot here for this description. So first, the deterministic algorithm actually allows us to ensure that we have invertibility. So that allows us, once we have actually given Bob an encrypted message, that he can actually get from the encrypted message back to the original data we wanted to send. Next, we have a fixed number of bits. And this seems kind of antithetical to an arbitrary size of block or input. So what we can do is with our message, we can break it up into blocks. I just cannot write now. This is why I use slides. So we can break it up blockwise. Let's call this 1 instead. 1, M2, M3, dot, dot, dot. So we don't want to change anything about the message so much as partitioning it. So then when we have our encrypted message, which will be represented by the ciphertext, it will be very similarly partitioned in such a way that we can just concatenate everything together to be our entire message. So we've solved the problem of fixed number of bits. We can do arbitrary sizes with this just by padding the last so it is block aligned. It's a big subject to try and do in 3 minutes.
Feedback? You were super clear and didn't you weren't monotone, but you didn't talk too fast or too slow, which is really nice.
Became a panic speller though. That was a problem.
I liked how you wrote things out on the board. It'd be really helpful for a note taker.
I think sometimes you had some issues writing stuff like that, but you definitely shook it off really smoothly.
Mm-hmm.
Other comments? How about some constructive criticism?
You talked into the board a little bit.
Yeah, I feel like that was an unfortunate side effect of having to try and write so much. It's hard to fight that one. Slide to my answer.
So you said you use slides, but if you're doing something on the board, maybe have some notes those spelling errors and all the verb.
Yeah. Confidentiality, I would have found confidential next time.
Although it occurred to me that misspelling Alice actually kind of loosened the audience up a little bit. Everybody kind of chuckled, and you could imagine intentionally misspelling things. Trying to get people to loosen up a little. Other comments? Thank you.
Hi everyone. Today I'm going to talk about linear functions. So I would like to start with an example for us to make sense of the definitions of linear function. So let's say that we are a car company. So we make car. To make one car, it costs us $10,000. So for one car, we would spend this amount of money. So what about if I want to make 2 cars? How much will I spend? Anyone?
20.
Yes. 3 cars would be 30, right? So if I want to represent this in a graphical format, I have 2 axes, which represents the 2 variables. So one is the quantity of cars, and the other is the amount of dollar. So for 1 car, I spend 10,000. For 2 cars, I will spend 20. So each of these represents a point in this 2D space, right? So if I link up all those points, I get a line. And that's where linear functions, that's why we call it linear function. So the relationship is linear, sorry. So, which means that if I change a quantity, I will change the other by a fixed amount, right? So this could be, so we could get a formula. If we call the amount y and the quantity x, y is equal m of x. M will be the slope of the line. Right. So what about now if to produce our cars we need to spend a fixed amount, maybe to buy the factory or, I don't know, to buy the machines? Then this means that at the beginning, let's say that it's $100. So we would have to spend $110. Okay.
Okay, so positive feedback.
I like the combination you have like the table and the graph, and like how they both really go together well and reinforce each other.
You spoke super clearly. That was really good. You didn't mumble at all.
And I really like how you used an example to like introduce the topic.
Any other comments? How about constructive feedback?
It's not really a criticism per se, but your choice of example kind of threw me off because, like, as an engineer or like as a mechanical engineer, when you were talking about price of cars, I was like, oh, she's going to talk about like economies of scale or something. And so 2 cars is going to cost less and 10 cars is going to cost less.
So that would be a sublinear function.
Yeah.
Well, yeah, I teach a math class for freshmen, so it's pretty basic.
Any other comments?
I think if you had defined some vocab, like written out like slope and wrote it out in terms of like, oh, how much it changes and things like that would have been a little more helpful.
Just a very minor thing. Like, I can still hear you in the back, but maybe just a little bit.
Oh, yeah, about that. So if you don't have a microphone in your section, like it might be pretty hard because you weren't talking that loud, and with a microphone it was fine.
Just work on projecting your voice.
Yeah, I had this feedback before.
Yeah.
I'm trying to work on it, but there's too much work to do.
Okay. All right. Any other comments?
let me know when I should start. Okay. Hi everyone, can everyone hear me? Today we're going to talk about Git. So who here has used Git before? Raise your hands. Okay, we're going to pretend that you haven't, okay? So for the purposes of this demonstration. So what is Git? Git is a distributed version control system. It is a way for you to track changes to your files after you've modified them and save a history of all of your changes. It's great for software development and working in teams. So Git is very powerful, but today we're just going to talk about some of the basics of Git. So let's start off. Let's think about this analogy. This is my favorite analogy for Git. Think of Git as a photographer. The analogy is not perfect, but bear with me. So let's say we have a repository. And this contains all of your files for your project that you're working on. Let's say I add a file, a.java, okay? And so first thing you have to do is you have to use git add and then the file name. So what this does is this tells Git, okay, hey, let me track this file from now on, all right? So once you've tracked that file, next you want to commit it, and then write a message, a commit message. And this commit message just tells Git, hey, what did I do for this particular commit? And so this step is equivalent to a photographer taking a snapshot of your repository at this given moment. And so now that we've taken this snapshot, say we make a change to a.java, right? And then now we have to go through these two steps again. We have to first add it, and then we have to commit it. And now Git will take another snapshot, okay? Who is the photographer here by any chance? Yeah? Okay, great. Do you have all of your photos on your camera? No, that would be bad, right? That would be terrible. What if your camera breaks? What if you drop your camera? All of a sudden you've lost all your photos, right? It is the same thing for Git. If your computer crashes, then you've lost all your files. So Git provides a way for you to push your code to an online repository, a remote repository of some sort. So what you can do is you can use the command git push and then specify your remote repository right here. And this is equivalent to you uploading your photos that you just took with your camera online somewhere. And similarly, if you ever want to download files from your online repository back onto your computer, then you can use git pull. And this remains the same. So one last thing, if you ever wanted to go through your camera roll and look at all of your commits, then you can use git log. And that's about it. So yeah.
Okay, so positive feedback.
I think you did a very good job interacting with the student. I think it's hard to interact with students when talking about Git, but you still did it. But with the example of camera, that's pretty good. Yeah.
You're really enthusiastic and super easy to understand.
Other comments? Any constructive feedback?
So I didn't get very much of this, and it was probably just because you're talking to us and we already know Git. But I kind of got a vague, this stuff is kind of easy vibe, and I don't know, it's probably fine, but at the beginning it almost seemed a little sarcastic. And if I were a scared little freshman, it might affect me.
So just follow up to that. Would it affect you because it seemed like this was being watered down, or that when you tried to use Git, you realized, oh wait, there's a couple of other things I have to do before?
Oh,
this?
no. The content was all good. It was more oh, I'm dumb for needing this being explained to me.
I don't think I really got that. I think if I was when I first learned it, I was super overwhelmed, and it was I didn't understand what different commands meant. So I think this is really helpful for that.
I
comment, it's not really like constructive more as much as it is positive. But when I took this class, I don't think my TA explained it even in like half as much detail. He was like, oh, like, you can read this later. Like, if you don't get it, it's your problem. So this was great.
I kind of wanted this to be like on Teach 61B, so
Yeah.
they've just learned it. So this is my analogy for teaching them. So, yeah. But everyone here knows it, so.
All right, cool. Thanks.
Hey guys, I'm Yawen, and today I'm going to talk about Boolean operators and short circuits. So imagine you type this in the terminal, 1 divided 0. What do you think? Like, what will happen when you type this in the terminal?
Error.
Yeah, we're gonna have 0 division error because you like divide 1 by 0. But what if we put 2 or 1? Sorry. 1 divided 0. Like, imagine I'm using the terminal. I probably like put this in the terminal and then like click return and it shows 2. So why it does not show the error? Because we have OR operator here, and because of the short circuiting, it tells you that, okay, this is 2. We have already seen the 2 like in front of OR, so we will like we will not even look at this. So that is short circuiting. Short circuiting happens like when you have OR operator or AND operator. When it comes to OR, it returns the first true value, or it values like all the operands until it like hit on the last false value. So say we have like false or false or false, like all this kind of, it will return like the last false. But what if we have false or true or false, it will return the true here. And similar things applies to AND, except that when it comes to AND, we will return the first false value, or it returns true until it evaluates like all the operands. So example including we have 2 or 2 or 2, so it returns true because of this, and 2 or false or oh sorry, it's AND here. It returns the false here because we see the like first false. Okay, that's pretty much it.
Is there feedback?
I like that you had a lot of examples, especially with the OR and the AND. Like the examples kind of complement each other, and so that was really cool.
Yeah, and I like that with each case you explain the case where it had to go to completion. So that contrasts the two.
It's also nice starting with an example like divide by 0. Because Cameron's like, oh, that's going to be a problem, right? And then you do this next line, which is like, oh, wait, that's not a problem? Oh yeah, I guess that makes sense. It's kind of, it creates a situation where you get people engaged and expecting things a certain way, and just following things sort of turns it around. Other constructive criticism?
that you had written like or short circuit when like it hits the first true value, or it keeps like I wish you had written a little bit of that out, or like and keeps going until it hits a false value, so that it would be more clear in terms of your examples.
Any other comments?
This is just like a minor nitpick, but like I think if the or and lined up, I think it'd be better because it's kind of confused. Like it looks like there are 3 and examples and only 1 or example.
Yeah, I guess I should like put the.
Yeah, it's only like small.
Any other feedback? No? Thanks.
Totally fried today, so this might be completely frantic, but we'll see how it goes. So last class, you guys saw the Y Combinator. So just as a reminder, I'm going to write it out here. And this is similar as well to the Omega Combinator, which we saw in the previous class, where it uses self-replication. But in this case, we're threading through this F function as well. OK, so I just want to go through an example to kind of motivate how this works and why it's correct. So let's try a factorial function. So in a language where you can name functions, let's pretend that's something like this. So I'm kind of mixing lambda calculus notation, just adding this naming, which is not in lambda calculus. All right, so in this example, you can see, because you have a name, you can call the recursive function. We can't do that. So how are we going to get around this? Well, we can just introduce a variable for that. So I'm going to just rewrite it as this function now has this g variable. The rest is the same, but now you're calling a parameterized function. OK, so what do we give this g? What is this g? What do we plug in here? Well, we can look at our model, see what does it say. We give f that double application, which, sorry, let me back up. Since this is a function application, we are plugging this into the x's. So we know this is our g. If we evaluate this now, it becomes n. Can I just write it just because people might like it? So just because you have this here now, these two x's would expand to both of those. So whenever you're calling this function with a number, it would either go to the, oops, I forgot the one, sorry. If it's 0, it would go to the base case, and every other number, whenever it goes through this call, it would use the self-replication to keep introducing the recursion. So you can always complete, this function would always complete.
Feedback? I appreciate the big handwriting.
I'm honestly impressed with just how fast you wrote some of that stuff up there. I wouldn't be able to. It's like impressed.
It is super, like, I feel like this is not very separated from this. These should have been clearly further apart, but yeah.
Other feedback? Okay, so constructive.
I don't know, I mean, it's not necessarily criticism, but like, this seems super complicated. As someone who didn't take 61A, I'm now reevaluating the course in a new light. Like, I didn't get any of it, so.
Yeah, sorry, I started with the premise that we've seen at least lambda calculus where you only have variables, function definitions, and function applications. So I kind of glossed over that.
This isn't 61A stuff. This is lambda calculus.
I have no idea. I have not taken those classes.
Yeah, so this is
Oh, wait, which class is this?
You shouldn't have said that.
Which class is this?
Lambda calculus.
I don't know.
Oh, okay.
I have not taken or taught something this in a class here.
Okay, I'm.
Oh, okay.
Yeah.
Now you must know where you went to undergrad and what class.
University of British Columbia, it's like third-year programming languages.
I feel better about myself now.
So this is how you define recursion without recursion. Church Turing thesis. All you need in a programming language to have full Turing completeness, full expressibility, is variables, function definitions, and function applications. Like, this is all anonymous. There's no naming.
Wow.
Complete equivalent to Turing machines.
Cool. Thank you.
She dropped the cross.
She dropped?
Yeah.
That's okay. All right, so Andrew.
No, I think someone set the precedent to just speak loudly, and we've been going with that ever since. Should I? Hello? All right, so one of the more interesting questions in astronomy is, given the size of the universe, where's the other extraterrestrial life? Like, as far as we know, we're the only intelligent civilization in the entire universe, which is crazy to think about given the size, considering there are billions of galaxies with billions of stars each. And this question, people attempted to think of an answer to this question in the first SETI meeting back in the 1960s. And this equation, which is very similar to Fermi estimation, was presented by the astronomer Francis Drake to try to get people thinking of what are the variables behind intelligent life in our own galaxy. So today I'll be talking about the Drake equation, which looks something like this. So n, which represents the number of intelligent civilizations capable of communicating throughout the universe, is equal to r star times, and I'll explain what the variables mean later, r star times fp times ne times fl times fi times fc times l. So let me quickly go over what each one of these variables stands for. So n is just the number of civilizations that can communicate. R star is actually, I think this is really cute, is the rate of star formation. And FP is the probability that there will be a planet given a star. NE is the number of habitable planets. FL is the probability that life will arise on a habitable planet. FI is the probability that there will be intelligent life. FC is the probability that the intelligent life will be able to develop like communications. And L is the length that this civilization will exist. So if you do some dimensional analysis, you'll see that this will work out to number of civilizations. So the rate of star formation will cancel out like the time component of the length of civilization. And the original estimates presented by Francis Drake get you approximately a value of, well, actually, it's not that interesting. The original values aren't that important. But basically, the end-up number is if you use conservative estimates, you get 20 civilizations in the galaxy. And if you use like the most optimistic estimates, you get like 5e to the 6, I want to say, civilizations in the galaxy. But that was in 1960, and people did not know as much as we do now. So modern estimates of these variables include, for rate of star formation, it's about, but modern. Modern estimates put, like, if you use the most conservative estimates, you have 1e to the 1e negative 9, which means we would be the only, like, probably only civilization in the entire universe, or we can have, like, 150,000, which then, like, presents the, like, Fermi paradox, which is, where are they if the estimate is so high? Or I guess if you are a pessimist, then we're the only ones.
It was a very interesting topic. And I like that you write very big on the board.
Thank you.
I liked your comment about our star being cute.
Other comments? Quick constructive feedback.
You started out writing large, and then you just got smaller.
Oh.
Probability gets smaller.
It's like a really tiny quibble, but for the number of habitable planets, you just said number of habitable planets, not probability that a planet is habitable.
Yes. Wait, no, number of habitable planets. It's actually a number.
It's just a number, but
Yeah,
why are you multiplying it by the probability that there is a planet?
Probability of, it's like the probability a star has, I should have been more clear. It's a probability that a star system has planets.
And then that's just the number of habitable planets per star system?
Yes.
Okay.
Any other comments?
Nice. Thank you. Oh, yeah, actually.
Hi everyone, my name is Bhavna, and today we're going to talk about something that we saw pretty briefly in lecture, known as Gaussian elimination. So, quick show of hands. I'm just going to say, like, I'm not writing out the whole thing. Quick show of hands, how many of you guys have seen this before in 54? Great, okay, so we're going to do it again in EE375 for those of you who haven't. It'll be quite interesting. So, there are 3 essential rules. The first one is that we are allowed to multiply by, so these rules basically tell us what's allowed and what's not allowed. So what's allowed, the first one, the most basic one, is that we're allowed to multiply by scalars. The second one is that we're allowed to swap rows. And I I guess the intuitive understanding behind the reason that we're able to swap rows, which most of you didn't see in 54, is that swapping rows doesn't change the order in which we write equations, so it's still totally a valid system. And the third one is that we can add a scalar multiple of one row to another. Great, so now that we've seen this, let's just work through a really quick example. I know that we saw 3 types of system solvabilities, unique solution, infinitely many, and no solution. So let's try to solve these set of equations. So 49x plus 7y is 49. 2x. Great, so this is equation 1, this is equation 2. Let's put it into a matrix. So we have 49, 7, 49, 42, 6, 42. Let's divide the first row by 7 and the second row by 6. So we have 7, 1, 7, 7, 1, 7. And then let's subtract R1 from R2. So we have 7, 1, 7, 0, 0, 0. Okay, great. So at this point we can stop because we have a full row of all zeros at the bottom. And as seen in lecture, this is basically characteristic of infinitely many solutions. So that means our solution system is going to be in the form of a line. And in vector notation, does anyone want to tell me how to write that? Great. So it's so basically the way it works is 7x1 plus x2 is equal to 7. Let's pick this to be the pivot, this to be the free variable. The answer then works out to, I'm just going to skip ahead, so it works out to 0, 7, and plus a minus 7, a.
Okay, so let's repeat that.
Enthusiastic, and you were on the steps, which or not the steps, but like the rules, which I thought was helpful before you started the exam.
So a couple more hands.
I was just gonna say you were super peppy, which is great. We all really needed pep.
Especially this late.
I thought the board use was really good, and it's for thinking about taking notes. It can be easy to follow along.
Any other comments? Some constructive feedback?
I guess the quibble, you didn't say that the rules were for matrices at the beginning. It was probably applied, like all of us got it. But I don't know, if I had never seen elimination before, then maybe, I guess, mention that there are rules for what you can do to the rows of the matrix. I don't know.
Okay, for sure. Yeah, so specifically to rows of the matrix and not like to the whole matrix then.
Yeah.
Okay, yeah, for sure.
Any other comments? No? Okay, cool. Okay, so Michael D. Interestingly, we had 3 people in 17 minutes before 6:30. Chance we might actually get done on this list.
Hello? Hello? Cool.
Hi everyone, I'm Michael, and today we're going to talk a little bit about what is known as a replacement algorithm. Replacement. So imagine this. I am an artist, obviously very talented, but also very busy. So what my goal is to create as many paintings as possible in the shortest amount of time. And what kind of artist would I be without my trusty palette? And so my problem here is that on my palette, I have only 3 slots available for different colors. But in my paintings, I'm going to be using a bunch of different types of paint. So my problem is that when I want to use different colors, let's say I wanted to create a painting, and I'm going to use red, and maybe some blue, maybe some green. And if I want to add some yellow into the mix, I don't have any room left, so I have to choose one of these colors to replace with the new color yellow. And the problem is that that replacement takes a lot of time. I'm going to have to unscrew the paint, and I'm going to have to clean some stuff up and stuff like that. So I really want to minimize that as much as possible. And so we could think of a few approaches that we can use for our replacement algorithm. For example, maybe I just choose one at random. So I go eeny, meeny, miny, mo, and I say, OK, let's replace this guy. And if we can think of some pros and cons between for that algorithm, for example, it's completely random. So on the average case, we're going to get the same performance every time. Maybe it's like some medium level performance, but maybe we can do better. So what we're going to consider is that as a painter, maybe I am actually going to be using paints kind of more frequently together. So if I'm using red at one point in the painting, I'm going to be using it again pretty soon. So we have another type of algorithm called least recently used, or LRU. And this is a different type of replacement, such that if I were to use red, yellow, and then green, and let's say I wanted to add some blue in, the last one that I used was red. So then I add blue in. And the benefit of that is that we get to take advantage of this temporal, what is known as temporal locality. And we can be more efficient in choosing which one to replace. So now, because I used green most recently, it's a pretty high probability that I'm going to use green again. So we can consider these different approaches for their pros and cons and select one that best fits our needs. And we can extend this to an example like, let's say, an operating system. We have a disk, and we have memory. So if we want to page in things from disk to memory, then we can choose which pages to replace based on this algorithm. Thank you. Thank you.
I teach the same class, and I really like the analogy, actually. So I really like the analogy.
Thanks.
Yeah, I'm in the class, and I really like how you started off on like a light note. Like, it really made it easier to like listen to.
Thanks.
Other comments? So constructive feedback? I thought your paintbrush was a rose, actually. Scepter.
I'll label it next time.
Is that all we got? All right, good work.
Thank you.
Okay, Michael C.
Hi, everyone. I'm Michael, your GSI this semester. Today, I'm going to teach you, introduce Snell's law to you, which describes how light is bent at the surface between two media. So, Snell's law. Consider there's an interface between two media. And each of them has their own refractive index, N1 and N2. Consider there's a light ray coming from the left. and it incident at the surface for a certain angle, theta 1. And it turns out that the light ray will bend when it enters to a different media. And Snell's law basically tells us like n1 sine theta 1 equals to n2 sine theta 2. So if you know 3 of the 4 variables here, you can predict the rest of it. So let's say n1 equals to 3, and theta 1 equals to, 30 degrees. And n2 equals to square root of 3. Can anyone tell me what's the output angle of this light? Okay. So let's work it out. So we just plug in a number, 3 times sine theta 1 is half, equals to square root of 3. So we know that the sine theta 2 is like square root of 3 over 2. So the output angle is 60 degrees. So this is the first situation. Let's consider a second one, that if n1 stays the same and the incident angle is still 30 degrees, but I tell you that the output angle sine theta 2 equals to 3 over 4. Can anyone tell me what's the refractive index of the second media? So it turns out it's 2. So this is a very powerful, simple equation, but it's really powerful. You can trace the light if you know the refractive index of the media and initial incident angles. Or you can measure the refractive index of a media if you can measure the output angle of the light. That's all. Thank you.
I really like the topic, and I'm glad you made it to both situations, and you have a really nice concluding sentence.
Other comments? Any constructive feedback?
Oh, positive. You wrote like pretty big and nice and clear, which is good. And you didn't let the fact that none of us could do simple arithmetic lose you.
Clearly you needed differential equations, and the audience would be far more engaged. Right, any other comments?
Do you ever intended to explain why this is the case? Like, what's the principle behind this law?
They'll be covered in the next class.
Right.
You called it simple, but no one in the class answered any of the questions. I don't know. That could be a little insulting.
I think nowadays people use computers right now, so it's fine.
Siri.
What is it?
Some of you will go and solve this problem. All right, thanks very much.
Thank you.
All right, Amy. She's just getting ready for my lecture. She's trying to get ahead of everything here. All right, so yes, you can. We have a Mac. Okay, yeah, so you should be able to just plug right in, I think. Can she use the projector? Pink marker? Yeah. Is that yours? Really? I've never seen a pink marker before. You did?
Someone took the right one, so I did not down.
I see. Sorry.
Is there anything for, okay.
Is everyone here signed up for attendance? Yes?
I didn't.
Haven't. Okay, where is the attendance sheet over there?
Okay, guys, so before we get started with this lab, I just wanted to go over a quick overview of how to breadboard one of the first circuits you guys are going to be building. Just so you can remember, the breadboard is organized so that these outermost columns are basically organized so they're all connected together, usually for power rails, and then these internal rows are basically all connected horizontally, and that's typically where we're going to be putting our components. So the circuit you guys are building is this simple current mirror here. And the first step in breadboarding, we can choose basically where we're going to put our power rails. So by convention, we'll put our positive rail over towards the red, and the negative rail can go over by the blue. Now, one of the trickiest parts of this is just figuring out what orientation to put the BJTs, the discrete 2N3904 BJTs that you have. So one way I like to remember it is if you put the flat side facing you, then it's like it goes EBC from left to right, kind of like ABC, like the alphabet. So first, let's think about how we're going to place Q3. The emitter, base, and collector of the BJT are all oriented from bottom to top, which means we want the flat side of the BJT facing the right-hand side of our breadboard. So that's where Q3 is going to go, and then we can look at how Q3B and then Q4 should be placed as well. Now, the tricky part about this is that even though you see how Q3 and Q4 are sort of mirror images of each other on the schematic, they're actually oriented the same way on the breadboard, so just be careful about that. Now, lastly, we can hook up our power rails, first the negative supply, then tie the bases together, then add our resistors finally, and then just hook up the power supply. And then we're done. One note before you guys get started, it's a lot nicer if you take the time to trim the wires. There are wire cutters at your lab bench. So something like this is going to be a lot harder for both you and me to debug. So try to do something like this if you can.
Positive feedback?
I wish that my EE40 lecture or lab had been like even a tenth this prepared. We were kind of just like, here's some parts, have fun. Because yeah, this is really good.
Setting a high bar for the other.
I like how the PowerPoint went step by step, and you highlighted the components on the diagram on the left, as well as the components you placed on the breadboard on the right at the same time as you progress through.
Yeah.
I mean, this is more of like an instructor thing. And while you set an unrealistic beauty standard for your circuit, I think it's really good that you did that, because having to debug those circuits that people have like spaghetti wires on, in there, it helps them as well as you.
I like that you gave sort of like mnemonics for how to remember how to place things correctly. That's helpful.
I also like that when you said convention, a lot of instructors just assume students know that, but you actually said explicitly what the convention was, so that was really nice.
Constructive feedback?
Actually, it's something. Yeah. From what I know, whenever you're being recorded in video, the people watching at home can't see when you walk up to the screen.
Okay.
So sometimes it's better to use your mouse to point at stuff on your screen.
Okay.
And that gets recorded along with it.
Cool.
Yeah.
Or laser pointer or something.
All right, any other comments? Cool, thanks. And shockingly, we finished before 6:30. All right, nice work. Okay, so let's take a few-minute break. See if they're still in there. Yeah, or if they get kicked out.
Wait, repeat. I was like, wow. I was like, wait, who's an officer now? And I went and looked, and it literally was like, I was like, oh,
Yeah.
I know him.
Yes, I mean, I try not that picture my face there.
Yeah. Well,
And then we're going to do
I got the
flow.
She's a householder. Yeah.
Did you do first semester?
Yeah.
Like
Very long
semester
time
that
ago.
done,
Yeah.
like probably freshman year or something.
There's a book like, oh, yeah.
No.
Yeah.
Let's be honest.
Yeah. Let's be honest. We've been at freshman year, so.
I did the first semester stuff over.
Great, yeah. I was international. Pull up your thing. You don't have.
You got it the first semester?
No. How did I get it the first semester?
Okay.
But like slowly. Like now I would definitely say like to any troubleshoot that.
Yeah, I mean, honestly, I think it's
It's like a formula style card, but it's smaller than a full-size one.
So like
that's what
we're
yes. Yeah, we use like all
we're working on it.
So have a company use rotary items.
We can have normal combination of all the previous.
I'm not gonna say you're wrong because I can't.
Yeah, so that's why we're using air restricted as part of the compliance. So we actually can't put more air. So we can't use it. Like we can't.
Yeah,
I was like, Dad, maybe we're
So
yeah, like we're working on it. Like we're trying to. There's like a lot of.
I really should have. So I'm not on the engine, but I really should have. Because I run with the drive lines.
Besides planning and like also like
I don't know. It's a free
do some basic. Like you try not to do
our output for.
I mean, I did it
In first gear, it's like 700 pounds.
Yeah. It's a goal since semester.
No, it's fine. No, I was like,
It used to not be when we ran it, but I think we're putting one in this year. Because we just moved to the new engine from a 250
So that was
2
interesting.
years ago.
I guess Harris was first one.
Yes, it's okay. So you guys are
Like, no, I was thinking you said something like this.
Is that we still have to put the air through the same thing.
No, because you have speed joint.
So, yeah, so,
But yeah,
like you,
like, sorry.
It's okay.
you can't use a
It's
turbo
okay.
to bypass the
Yeah,
flow
it's
restrictor
fine.
that you have to upgrade.
But yeah.
So it's like,
Yeah, but like,
I definitely
glad that you guys are working on it.
but it's not as helpful as it would be on a real car.
With the same display, like you have 700. The rotary item will give one more.
they have a still
It just sat there. Like,
So
I was
it
like,
could be much more.
we just
You guys can come to like fire on
So,
Alright, so 5-minute break.
Those who are
You guys want to stretch your legs?
it looks
I have
so
that.
much better. Yeah.
And you have a management.
Thank you.
we use like a recluse clutch.
I'm not sure what you would
It's
know.
a pneumatic clutch.
And what about, are you allowed to have a nitrogen?
I always read about sound like CUI.
Oh, I think I should know. He is cool.
Yeah, it was like
Yeah. Oh, okay.
I know we built it.
He's cool.
Yeah, he's cool.
So the upward trajectory.
Yes, like if you know, if you knew this guy named Jacob.
So you're a
Yeah, he was VP.
I've been with the team for 3 years now.
So
Yeah, we improved in VP
So have
this
you
semester.
ever been
Like it's
to
genuinely good.
Yeah, 3 times.
Okay, so keep like modifying.
One of our
Yeah, it's always like
Entirely red hard.
He's awesome. Like I'm like.
But I mean, you have some like basic like, knowledge of how to do it.
He's pretty
So
sure.
you can just, I mean, you have something to work on. It's not
He's in every
from.
Yeah.
No, we designed it.
Well, I mean, like,
so we built it around.
Oh, yeah.
Like we well run. We like the only things we buy
You buy suspension shocks, you buy brakes, you buy the
it's like my phone doesn't
you buy
read in time. So I look at what email someone like point out.
It's more of like
I would
skill set.
Yeah.
And
You feel
so what do these
So our team is pretty like famous for being super light. So a lot of cars, they try to build up like 500.
So I think what happens for me is I really want cars, even though I ended up
all our cars have been under 400.
I've never
we jumped up so the lightest beat. So
that sucks. I mean, I feel like a lot of
you were the lightest car to finish. It was 200
without you, I have like 100 students without a TA.
But after that, we had
more than
100.
that would be
Yes. So yeah, right now we're like a very strong team, not like
I'm just
number one, but top 10. We got number 4 in design last year.
You're high. You're high. Okay, you're good. If anything,
And then you have your grades.
Even if like they don't do anything, it would at least take a semester to process that.
You need a lot of like down pressure.
Yes.
You need to have a huge weight.
I mean,
yeah,
you need
so,
yeah, I did look at your website, just search some.
Yeah. I basically yes.
So much more.
This guy's
Actually,
Oh, this one.
Yeah, I don't know.
Is everyone sitting here? Oh, another sign-in sheet. Should I sign this one too?
I think you can pass this pen around. It's not
Oh, I like this pen.
Your pen now.
Maybe. I haven't
I don't think we need to sign it. Since we already signed the average.
I know. I just want to what if I get 2 points?
You might.
We won't know.
I think I was on the other day. So I was on.
And it's sketchy because you're student together.
What did you write? You write Adam after go?
Yeah.
I wrote Bob after go.
Okay, so I have a sign-in sheet for people in room 2. Hey, if we end sooner, we can go home sooner.
If we start, we can end earlier. Thanks.
All right, so where do I find the list of people who presented? You took it? Can you send me an email? Thanks. Okay, so there are probably a few more folks that didn't present. I will send instructions out once I kind of tally everything up. Hopefully not a huge number of people. Let's see here. Also, we have the sign-in sheet probably wrote still. So if anyone did not sign up yet, make sure you get on either this sign-up sheet or that one. Is anyone not signed in yet? Okay. All right. Okay, so we will have a very short lecture today. We're going to do more of these after lecture, but I think probably won't have a whole lot of time to do that. So I think we should just skip that, just finish the lecture. 1 or 2 extra people, I'm not sure will make that much of a difference. Okay, so one thing is, have you guys all taken the professional standards for ethics? Yes, you should have done that. I think that is something, yep.
The course said it was going to be 5 45-minute modules. It was way longer.
The course, you can't believe that. So, you know, the number of times I've taken these online things, they always say, yeah, if you, so I asked my colleagues this question. Okay? I know this is being recorded, but, so I took, so when I started, it's like the barrage of, you know, like this and that. I'm like, wow, I'm like reading through these things. And so how is it that anybody gets these things done in like an hour? Because I spent like 2.5 hours doing this thing. And they're like, oh, you don't actually read any of the things. You just click the buttons, and if you get the answers wrong, you try again. I'm like, wait, that doesn't sound right. So I don't know how people do it in the time that they say. I've just gone through it myself. Apparently, I'm applying the wrong strategy as far as some of my colleagues are concerned, but I don't know. I agree with you. I think it's ridiculous. I think there's like too much compliance stuff, but some of this is pretty important too, though. Okay, so, oh, whoops, sorry. Okay, so, wait a minute. Okay, so designing good homework assignments. So we're going to chat a little bit about how we, some best practices basically for doing homework assignments. Okay, the first is figuring out what you're trying to do, right, with the homework assignment. So what are the goals? In particular, what are the concepts that you're trying to emphasize, right? What are the specific principles that you're trying to test? And so this is a good thing to talk with the instructor about. They will oftentimes have, you know, some feedback on this. Looking at old problem sets is also another way of, you know, getting some ideas. We'll talk about not reusing those old problem sets. So it's good to get to use problems that test both qualitative and quantitative aspects of what you're trying to teach. And these things are testing different aspects of it, right? So one is a little bit more oftentimes conceptual. The other is sometimes a little bit more rigorous. But they're both important. And oftentimes that, you know, these two things are complementary. And so if you have a good conceptual understanding and you have the ability to derive things or dig into them or apply them, you want to, you know, try to test both of those things in homework. You can use old problem sets to get ideas for problems, but you should avoid reusing old problems for a whole bunch of reasons. One is that the stuff just ends up on the internet. People collect problems. It ends up being actually quite a low bar to go and find solved problems from previous terms, and so people tend to do this. It reduces, of course, learning effectiveness. It ends up creating all sorts of problems with regards to cheating in the classroom. So avoid doing this. Of course, you know, you're going to have to change some. You know, some of the problems will be similar, ideally not exact, ideally not trivially, you know, altered. Also, if you think that you're just going to get the problems out of the back of the book, that doesn't work so well either, because the instructor's manuals are actually floating around. They're fairly easy to get as well. So really, there is a bar of originality for coming up with homeworks, and even so for test problems. And so it's actually very common to take last year's exams and, you know, give them as practice exams, or the last N years worth of exams and give them as practice exams. And so one of the things that you sort of kind of get used to doing is our job is to come up with original problems that are not trivial changes to the past problems.
Would it be good to use one old problem that they have a solution to, and then new problems after that to like build their confidence? And then also so they can like see how to do it.
Well, so maybe the question, I'll sort of turn this around and say, are there other ways in which you could achieve what you're hoping to achieve by using an old problem?
You can do a problem in a lecture, or you can do one in your discussion section, but not everyone shows up. So I guess it's like how much you want to help people.
Sure. I mean, you're also setting up a little bit of a Faustian bargain with the using an old problem, right? So think about how the effect of that. So the idea is, okay, they get confidence. How do they get confidence? The way they get confidence with the old problem is only if they go and get the solution to the old problem.
Well, maybe not confidence, but now they know how to do that one, and so
Okay.
then they can do the subsequent ones. on their
Okay,
own.
but how would they know to do that one, I guess is the question.
You could just give an example problem from the book and say this is the example problem from the book. Like, it achieves the same thing. They'll like find a workout problem and then they'll copy out the work.
Yeah, if they want to get some confidence. Another way of doing that is, releasing some problems and then releasing the solution a few days later, so there's not an impulse to go and look at the solution instantly. But I think the reality is, unless you have, some reason that people are going to be forced, if you will, to do the problem, there's not much incentive. And the question is, if you now give them incentive to do the problem, and yet there's an opportunity for some people to cheat and others to not cheat, you're sort of creating conditions that encourage unintended behavior. And so that's why my personal preference would be to say, to avoid doing that for that reason. If you want to provide, prior problem sets or exams, I think that's perfectly reasonable along with solutions, either right away or with. But I would say don't create conditions where, you sort of make it easy for people to do the wrong thing. Does that make sense? Okay. All right. Also, don't feel constrained by only problems that that are part of kind of what the class lecture covered. There is an expectation that people should be able to pick up things beyond what's in the lecture, and so if they have homework problems that requires them to, oh gosh, like open the book maybe, that's okay. That's fine. We are encouraging people to do more than only what they learn in class. Okay. So let's talk a little bit about, or continue to talk about kind of these questions here. So what are you trying to do? You're essentially trying to take concepts that you learn in class and ideally engage students in a way that's relevant. Right? So we tend to pick problems that have maybe practical relevance. I think Jeff Bokor teaches a class where you take apart electronics to understand what's inside of them. In every term, he says, I need stuff that's like current, not stuff from 5 or 10 years ago, because people just don't care about it. It's the same thing here. If you can try to tailor these things to, batteries, electric. I think there was an example about electric vehicles and, constant torque curve or constant torque no matter what speed you're on. Things like that. Electric cars. iPhones, stuff like that that's relevant that students will understand. That's great. Of course, that you can't do that for everything. The other thing is, sometimes it's tempting to come up with tests that are, trying to determine whether you got some corner case, some little thing. I think that's fine for a few problems that are, trying to differentiate the who really got some of these fine details versus not. But most of the, problems on tests should be really trying to understand, did you get the fundamentals, right? What are we trying to emphasize in the class? What are the key conceptual ideas, right? That's what we're trying to evaluate. Did you understand them? Can you apply them? And so on. So we talked about a taxonomy of learning, of different kind of axes of abstract, there's other things. recall is not a particularly useful thing to test. I mean, it's good, you know, and from a sort of baseline, hey, do you remember Ohm's law, you know, whatever. But in general, anything that you can easily look up is not what you should be spending most of your testing on, right? Assume that they could look it up, and so you want to think about kind of higher levels, and we'll get to that in just a second. The other thing is, make sure that the questions when you ask them, they're not that they're clear, right? There's times where questions can be ill-worded, it can have multiple meanings, so you want to try to debug it a little bit. You know, maybe if you write out some questions, make sure you get feedback from one or two other instructors or from other GSIs or other folks like that. It's easy to make one mistake that ends up causing confusion for everybody during an exam. So or during a homework. So try to tune them a little bit. Yep.
The exams were clearly not doable in the given amount of time. And I went and spoke to the professor that, you know, what's the point? And the professor says that we also wanted to test your ability to choose the right questions to do in an exam. I mean, I kind of get it, but I mostly do not get what that means. So what do you think of that practice? Like, is that fair?
So I don't think it's unfair. I'll tell you, there's a lot of ways of looking at it. One way of looking at it is life is going to throw you more things than you could possibly do. And so one of the key skills that you can develop is figuring out what you should do and what you should not do, right? So maybe you're lucky at this point in your lives where you can answer every email in your inbox. That point in my life has long passed. Okay? I tried to answer many of your emails, but I know I didn't answer every single one, right? I'm sure plenty of you could raise your hand like, yeah, you didn't get an answer back to me. In a startup, right, it's a life and death matter. Do I work on this feature? Do I call a customer? Do I make sure that the math is right on this thing, right? And so why I said is I don't disagree with that idea is that you've got to have this killer instinct, right? This is what's going to separate. Everybody's got the same 24 hours in the day, right? So what separates the folks sometimes that do very well with their 24 hours versus the ones that don't? It's that developing the killer instinct for which things should I work on. So you're doing this cost-benefit analysis, right? If I spend X minutes on this problem, then it's opportunity costs. I can't spend X minutes on some other problem, but what's the likelihood I'm going to crack this versus crack that? So those are all very, very useful kind of life skills. Now, whether it applies to do you understand optics 101, I don't know. But I think as a life skill, that's a very, very good skill to have. Okay? And it's one that maybe it's worth in the classroom giving students a little right. They'll have heightened emotional experience. Like I got through like 5 of the 8 problems. How many did you get through? I only got through 4. Okay, so remember this, right? The wording in your questions oftentimes will signal the kind of question it is. Are you trying to basically achieve recall, or are you trying to apply and synthesize entirely new things, or compare and contrast and analyze? And so generally it's a good idea to have a few kind of simple recall questions, get people warmed up a little bit, and have increasingly more sophisticated ones, perhaps ending with design problems in some cases. Build a circuit that takes a clock and divides it, and takes a 50 megahertz clock and generates from that a signal that has an on time of 20 microseconds and an off time of 70 microseconds, right? You can imagine applying a bunch of things to make that circuit, right? So things like that. So spend some time also thinking about how you want to grade these things. We'll look at rubrics in just a second. But you'll want to work with the reader, because they'll be doing the grading of the class, or the grading of the homeworks and make sure that the grading rubric and how you're trying to grade these, that you've thought through it, right, beforehand. Trying to figure out how to grade things. Some things are really hard to grade, right? The answers could be all over the place, you know, design problems that are not sufficiently scoped and you thought you were going to get, you know, a bunch of gates and instead you got a bunch of Verilog or you know, something. So think through, like, what are the range of possibilities? Another thing is sometimes, you know, students are not going to perform as well as they would have liked. And so giving them opportunities to make up points, you know, or a little bit of extra credit or something like that, that gives them a chance to illustrate that they've learned the concepts that maybe they missed. It can be motivating, right, because you're trying to make up points. It can also really aid the learning process because they haven't gotten the points. They've, you know, made a mistake. They're highly sensitized at that point to learning what they didn't learn. And so if you give them the opportunity to learn and recover some of those points, some really good learning can happen. Okay. Oops. So I want to talk a little bit about rubrics and grading. This ties in with the previous slide, and the idea is that you want to spend some time figuring out what are the kind of the 3 classes or 4 classes or 5 classes of answers that demonstrate approximate equivalence. So for example, you might say, okay, a particular answer, somebody demonstrates that they are, you know, developing some notion of competence, or they are actually competent, and, you know, what does that mean, right? So, or they're actually very good, you know, they're exemplary. Right? So figure out what those mean. You know, for a simple problem, what would be, yeah, you kind of got it. Like there's the, yeah, you definitely didn't get it, and you kind of got it. Be clear, right? You definitely got it, or wow, you got this really crazy corner case we didn't expect anyone to get. And so those gradations and writing those out as a rubric is really helpful. Sometimes you may not actually know what the rubric is until you get all the solutions. And so a very effective technique is when I have graded exams, I will oftentimes take the exams, do a sort on the answers, and cluster answers that are the same. So a bunch of people ended up with 101 microseconds, and a whole bunch of other people ended up with 217 microseconds, and somebody else ended up with 400 microseconds. And then there's like 10 people that got all sorts of answers. Like, well, okay, I could grade them in a random shuffle, or I could cluster them and see, did all of them make basically the same conceptual mistake, or were they correct? And so you may think you have the rubric up front, but you may actually, when you see the answers, discover that there are other errors or other insights. What's a total pain, though, is when that happens, is going back. Like if you don't kind of work on that rubric, in some sense you're doing a partial pass to establish your rubric, and then you're applying the rubric to those and subsequent problems, is that if you discover after you've graded half of them that there's these like other things that you weren't considering, now you're stuck because you're like, wait a minute, now do I go back and regrade everything, right? Or do I like try to kind of like ignore it, and then now I'm being unfair to some people, and other people maybe get like this extra point or lose an extra point for extra one. So one thing that actually helps with this, if you've used GradeScope, one of the faculty members here, Peter Abil, came up with this really great system where he, right, so many of you probably use GradeScope, right? Yes? Either as students or as instructors. The really great thing is you can adjust that rubric after you've started grading. Right? So that's, I think, when I think of all the things that GradeScope is good for, and then the cool thing is you make the adjustment and applies it backward to everything you've already graded. Okay? All right, so we are basically done. So be sure to fill out your peer observation forms and your teaching analysis checklists, and we're going to meet next. We're done for like 3 weeks. Okay, so yay, thanks for hanging in there with me. We're done now, and the next class is September 21st, so make sure you finish your peer review by then. I'm going to end because it is 6:59, but I'll stick around for a couple minutes if people have any questions. Thanks so much, and good luck in all of your classes.